So today we're going to talk about big O notation. Big O notation lets us talk about the growth of functions without having to worry about things like additive and multiplicative constants. When we're talking about the computation time required to achieve a certain task, let's say sorting a list of numbers, we're not interested in, for example, how fast your computer is or whether you have to turn on your computer. Right? Those are additive constants and multiplicative constants. What we're interested in is how fast the algorithm runs as a function of the size of the input. Big O notation lets us hide details like, well, am I using a 32-bit or a 64-bit processor? So let's get started and see what this mathematically means.
So this is going to be a definition. So let f of n and g of n be two functions. Okay, so we say that f of n equals big O of g of n, or just O of. Usually when we say O of, we mean big O. There actually is a small o. We'll get to that later. When the following holds, when there is some constant c bigger than 0, and some also x naught, which is another constant, such that f of n is less than or equal to c times g of n for all n bigger than or equal to x naught. Okay, that's what we mean when we say big O. So I'll give you a couple of other definitions. We also have f of n equal to omega of g of n, and that's we say that when actually f g of n equals big O of f of n. So basically, when you see big O, what you think of is that essentially f of n doesn't grow any faster than g of n. G of n bounds the growth of g of n bounds the growth of f of n, upper bounds the growth of f of n. When we say that f of n equals theta of g of n, we mean that f of n equals O of g of n, and g of n equals O of f of n. As a very simple example, let's just imagine we have f of n equal to, I don't know, n squared, and then g of n equal to n plus 1 squared, and h of n equal to e to the n minus 5. Right? If you plot these things, you see n squared, you see n plus 1 squared, looks like this. You have e to the n minus 5 probably looks something like this. Now, the important thing is that even though h of n lies below f of n and g of n, eventually e to the n is going to dominate both f and g. So it's certainly the case that f of n equals O of h of n, and g of n equals O of h of n, because h of n, this exponential, grows faster eventually. I mean, it grows faster if you, in the long run. These things will eventually cross. If I keep drawing these things, this guy will go above this curve eventually. But f of n and g of n grow at the same rate in the long run, asymptotically. Let's just do a couple of simple examples. So let's say that f of n equals 3n squared plus 10n minus 5n to the 2.5 plus 1.7 n to the 3. Now, I just want to point out a couple of things. A, it's certainly true that f of n equals big O of n cubed, because the leading term here is n cubed. So f of n, even though this function has all these other terms, the largest term is this one right here, right? And that's the one that we care about. And so certainly n cubed is, this thing does not grow any faster than n cubed. It's important to point out that because it grows as fast as n cubed, it also doesn't grow any faster than n to the fifth. So actually we can write f of n equals O of n to the fifth, right? But it's important to note that f of n certainly is not big O of n squared. N squared will not, even when multiplied by a constant, f of n will always outgrow any constant times n squared. Okay, so let's consider another example. Let's let g of n equal to 5 log squared n plus 7 square root of n. Certainly it's the case that g of n equals O of f of n. That's the f of n we have above. But f of n does not equal O of g of n, right? Because the leading term for g of n is the square root of n. One thing that will come up from time to time is needing to manipulate logarithms. And it's important to be precise here because it's easy to be off by constants, but because it's in the exponent or in a log, it actually will affect things in a different way. So let's just consider some examples here. If we have f of n equal to n squared and g of n equal to 2 to the 4 log n, let's try to answer whether what are the big O relationships here. Now, I want to make an important note here. So for convenience, when we write log n, what we mean log base 2 n. And also, when I write ln n, that of course means log base e of n. Okay, so that's just a little side note. So let's get back to this problem here. So notice that g of n equals, one thing we can do with this exponent here, one of the things that we can do to play around with this is we can take this and make this 2 to the log n all to the 4. You can take exponents that are products of exponents and actually move one of them to a higher exponent on the outside, right? And this makes our life a lot easier because now we can write this as, well, 2 to the log n is just n, right? 2 to the log base 2 of n is simply n. This just becomes n to the 4th, right? So hence we can conclude that f of n, which is just n squared, does equal O of g of n, right? But g of n does not equal O of f of n. Good, right? Okay, so let's try a slightly harder one. How about f of n equals 3 to the log base 5 n, okay? Now, of course, I picked these weird numbers, 3 and log base 5, because they don't match up appropriately, right? It's very hard for us to reason about how this thing grows. So what I want to do is to express as n to the c, this thing, for some c bigger than 0. Now, it's important for us to answer what that c is. If it's bigger than 1, for example, then this thing is going to be growing. It's going to be increasing in size. And of course, it's less than 1, then this thing will be shrinking. So it's very important for us to figure out what is the c in this case. All right. So, of course, so let's note that that 3 equals 5 to the log base 5 of 3. Now, this seems a little bit silly. I took the number 3 and I simply wrote it as 5 to the log base 5 of 3. But it's important to do this because now I've modified the base of the log in an appropriate fashion. So we can use this to observe that 3 to the log base 5 of n equals 5 to the log base 5 of 3. I'm just replacing this is what 3 was before, and now this is to the log base 5 of n. Okay? I can continue with this. I can write this as this equals, I can now just multiply these exponents together. This is 5 to the log base 5 of 3 times log base 5 of n. And now, of course, I'm now going to put this guy, I'm going to make this guy the first exponent, right, and this guy the second exponent, which I can do, right? This now equals 5 to the log base 5 n, all to the power of log base 5 3, right? And of course, 5 to the log base 5 of n, this just equals n to the log base 5 of 3. Now, this is good. So now we have it. This is our c right here. We've now gotten what our c is. Right, this guy right here. And what we can note from this is that log base 5 of 3 is actually less than 1, right? Now, it's less than 1 because the base is smaller than the argument of the log. So in this case, f of n equals big O of n.